Hello. So my voice is really small, and I don't want to. Well, I'm staying in my relative's house, and I will take a night in this place. This is an apartment. So to sum up, today is a good day. I spend much of the time in this apartment, and well, in the afternoon I have a short lesson in his house. It was fun. Then I get back to this place again to take care for our baby and clean the home, clean the house. Let's talk about an interesting topic. What is the coldest thing in the world? The coldest materials in the world aren't in Antarctica. They are not at the top of Mount Everest or buried in a glacier. They are in physics labs. Clouds of gases held just a fraction of a degree above absolute zero. That's 395 million times colder than your refrigerator, 100 million times colder than liquid nitrogen, and 4 million times colder than outer space. Temperatures this low give scientists a window to the inner workings of matter and allow engineers to build incredibly sensitive instruments that tell us more about everything that from our exact position of planets to what's happening in the farther reaches of the universe. How do we create such extreme temperatures? In short, by slowing down moving particles. When we are talking about temperature, what we are really talking about is motion. The atoms that make up solids, liquids, and gases are moving all the time. When atoms are moving more rapidly, we perceive that matter as hot. When they are moving slowly, we perceive it as cold. To make a hot object or a gas cold in everyday life, we place it in a colder environment, like a refrigerator. Some of the atomic motion in the hot object is transferred to the surroundings, and it cools down. But there's a limit to this. Even outer space is too warm to create ultra-low temperatures. So instead, scientists figure out a way to slow the atoms down directly with a laser beam. Under most circumstances, the energy in a laser beam heats things up, but used in a very precise way, the beam's momentum can stop moving atoms, cooling them down. That's what happens in the device called magneto-optical chaff. Atoms are injected into a vacuum chamber, and a magnetic field draws them toward the center. A laser beam aimed at the middle of the chamber is tuned just to the right frequency that an atom moving towards. It will absorb a photon of a laser beam and slow down. The slowdown effect comes from the transfer of momentum between atoms and photons. A total of 6 beams in a perpendicular agreement ensure that atoms traveling in all directions will be intercepted. At the center, where the beams intersect, the atoms move sluggishly, as if trapped in a thick liquid. On the fact, researchers who invented it described as optical molasses. A magneto-optical charge like this can cool atoms just to a few microkelvins, about minus 273 degrees Celsius. This technique was developed in 1980s, and the scientists who contributed to won its Nobel Prize in Physics in 1997 for the discovery. Since then, the laser cooling has been evolved to reach even lower temperatures. But why would you want to cool atoms down that much? First of all, cool atoms can make very good detectors. With so little energy, they are incredibly sensitive to fluctuation in the environment. So, they are used in devices that have underground oil and mineral deposits. And they also make highly accurate atomic clocks, like the ones used in global position lines. Secondly, cold atoms hold enormous potential for probing the frontiers of physics. Their extreme sensitivity make them candidates to be used to detect gravitational waves in future space-based detectors. They are also useful for study of atomic and subatomic phenomena, which requires measuring incredibly tiny fluctuations in the energy of atoms. Those are drowned out at normal temperatures, when atoms split around hundreds of meters per second. Laser cooling can slow atoms to just a few centimeters per second, enough for the motion caused by atomic quantum effects to become obvious. Ultra-cold atoms has already allowed the scientists to study phenomena like Bose-Einstein condensation, in which atoms are cooled almost absolute zero and become a rare new state of matter. So, as researchers continue in their quest to understand the laws of physics and unravel the mystery of our universe, they will do so with the help of the very coldest atoms in it. Okay, that's all. Yeah, that's an interesting topic. And goodbye.